I'm Nquire. I'm going to talk about the GRAPE algorithm, which is the Great Industrial Path Engineering, and it is an algorithm for path optimization. That's it's for to design pulses to make a quantum system evolve in the manner we want. So I'm going to follow this index, but I'm going to give a brief introduction to the topic, later and we'll explain the fundamentals of GRAPE, the theory, and also explain it with a quick example. And then I'm going to go to the main part of the research, which has been extending the GRAPE algorithm into cavities, which I have done with the valuable help of Mr. Número Salvador. Here I'm going to explain a bit the physics behind the cavities, the constraints that appear when we go to this complex equation. And I'm going to explain how to calculate the gradient, which, as we are going to see, is the most important part of the gradient algorithm, and show some results. Finally, so quantum systems are typically controlled with pulses in the microwave regime, and to compute implementing these pulses, we discretize them in time steps. We discretize in time propagator in n time steps. So if we have a spin pointing up, and the red line is a pulse which is going towards the system, when it starts to act on it, it will start to rotate, and at the end of the pulse, at the end of the evolution, it will be, for example, pointing down. And this is, for example, a pi pulse, where we flip the spin. There are two types of quantum control. The first one, and the easiest one, is the state transfer control, where we want to create a unitary that evolves just a certain state, a specific initial state, and it doesn't serve for any other state. So, for example, if we have in a two-level system the 1-0 state, we will only mine about the first column of the unitary propagator and not the rest of the matrix. Instead, with gate control, we mine about all the gate, all the matrix, and the gate control serves to evolve any kind of state we can have with the basis we have. So in this work, we are going to work with the first situation, the AC1. Let's start with the GRAPE algorithm. In a quantum system, we typically have an original Hamiltonian, the H0 Hamiltonian, or the drift Hamiltonian also called, which defines the system itself and the energy splittings that are in the system. And apart from that, we add another term. If we want to control this system, we add another term here, which are all the controls and the drivings. So if we have m control operators and n number of, and we discretize the time in n number of time steps, the control U is going to be a matrix of m times n dimensions. So here, what we see here is a control Hamiltonian, the kth control Hamiltonian. This is going to be assigned from 1 to m for the different controls, and this is going to be the amplitude in the time step j of the control k. So here, the GRAPE algorithm gives us a way of calculating the fidelity with some properties of the trace, and here we define two new operators, the lambda j and rho j, which serve to define the gradient with respect with the gradient of the fidelity with respect to each element of the control matrix of the U matrix. So here we have the fidelity with respect to U, K at time step J. What? UK is the, well, UK is a vector, is the vector of amplitudes for the control K. And then at each, this is going to be, the vector consists on n elements, which are going to be for each of them for a time step of the evolution.
So UK is all the time dependence in the
Yes, the time dependency of the U goes with the index J, and the K is for the control. It refers to the different control you have. If you have just one control, K is going to be just 1. If you have X, for example, sigma X, just is going, K is going to be 1. If you have X and Y, you will have K is 1 and also 2.
So for a certain interval is just a number, right? Or a couple of numbers or whatever.
Yes, for Kj is just one number. With 1K and 1J, it's a matrix.
And HK is
The control.
associated with each K parameter, right?
HK is the control, which can be sigma X or sigma Y or sigma Z.
And what is the rho F and rho T?
What? ROF, yes, ROF is the target state you want to the state you want to achieve at the end of the evolution, and the ROT is the state you are achieving when you evolve your system with this unitary, with the controls you have.
So rho F is the final one if you apply the exact.
No, ROF is the one you want to achieve, and ROT is the one you are achieving with your controls.
So you are optimizing.
Yes, yes, that's it. And yeah, from here you have to keep in mind that the GRAPE algorithm provides us a way of calculating the gradients efficiently, because here we have the formula how it is done, and if we were not doing in this way, we would need to calculate with finite differences, so we would need to calculate the fidelity at least 2 times for each gradient to make the rest at the end. No. Lambda is this, and rho j is this.
But then this metric, so this phi, capital Phi, depends on j, right?
No, because here you have the n here. So what they are doing here, this is like you have rho f here, and you can take this part to the right here, and this, for some properties of the trace, you can take this to here, and then you have at this side the state you are obtaining by applying the unitaries, and at the left side you have the target state. So it doesn't depend on J. Yeah. Yes.
Okay, so intuitively what you want to achieve is target which is close to the final one, right?
Yes.
And then you quantify this by this.
Yes, by this fidelity, yes.
And then you're looking something like a flat equal or something like this, right? Of this J and this right?
What?
So this is phi, right?
Yeah.
Essentially, you want that this phi essentially doesn't change, right? And then it's a point where everything.
Yes.
That's where the algorithm stops.
Yes, because then the gradient is going to be input to an optimization algorithm that is gradient based, like the gradient descent or the Adam or another alternative. Yes. Yes. What? I don't.
J in the right side and J plus 1 to n on the left.
Can you repeat? I cannot hear you.
You have divided the entire discrete U's into J plus 1 to n in the left and
Yes.
1 to J in the right part.
Yes.
Why?
Why? This is, you can also write like here, just in the left side, just row F, and in the right side, from instead of J, from n to 1, and here from 1 to n. But for some, I saw that there are some, the trace has a cyclic property that you can just take the operators from the right side and put them in the left side, and you have the same trace.
But I guess that you are dividing this because you are optimizing respect to control at time j at delta t.
Yes.
So then you have to choose the j on the right part of the equation in such a way that you divide it into this is the way that you choose the index j.
The index j, but this is here in this part, but this does not depend on j. The fidelity does not depend on j, just the gradient of the fidelity.
No, what I mean is that I think the question that I had and he was asking is how do you choose j?
J.
Because j, I understand that this is a trace and you can move it and there is no problem. But
Yes.
You are separating this into two parts.
Yes.
Based on the index.
And to calculate 5, no, you can whatever.
So
1, 2, 3, 4, from 1 to n, you can choose
sure,
whatever.
You have to choose it depending on because you are optimizing the control.
Yes.
J.
Yes. Here.
And you have to take the same one on the right side. Don't worry.
I mean,
I understood
here, here I changed the j to calculate to calculate the gradient with respect to the different elements of the matrix. But I go from 1 to n in j, and here then the j is different. I'm not sure if this is answering the question. I'm not getting the question.
What you are trying to do is to do optimization locally.
Yes, it's locally, yes.
Globally.
Yes.
You are transforming it into something that is local and sequential.
Yes, and separate. Yes.
And go to the right, probably to the left. So I understand what you
Okay. Sorry. So.
Basic question. What are the control operations? Are they parts of your tools that you can tune or something like that?
It's typically sigma x, sigma y, and sigma z.
Yeah, but what do you do about them? You choose the parameter of them, or do you choose which one of them to use?
Yes, I choose which of them I use.
So you just choose between using X, Y, and Z?
Yeah,
nothing in between?
No, nothing in between. No, because at the end, if you choose all of them, you reach to combinations of them. If you have like a coefficient times sigma x plus a coefficient times sigma y plus something times sigma z, you arrive to also to combinations of x, y, and z.
And in your propagator equation, which are the control operators?
This part is the control, and this Hamiltonian are the different operators. Okay, so let's go to the simple example. I have chosen as a simple example just the two-level system, delta sigma z. Delta is a detuning, and what I want to do is to train train a pi pulse that is robust with respect to this detuning. So to train the robustness, what I do is change the cost function from just the fidelity to a sum of fidelities, and for each fidelity I change the delta. So at the end, putting some weights to different deltas, I'm going to obtain the behavior I want. That's it. If I give high weights or big weights for this part of for these values of the detuning, I'm going to have more robustness. and if I give just a big value for the tuning in the center for the 0, I'm going to obtain a sharp peak. So this is an example, and the red line is what I obtained with the GRAPE algorithm, and the blue line is what I obtained with a top hat pulse, which is a square pulse, and is the fastest way of applying a pi pulse in this kind of system.
Then one question, because here I can imagine that you also took into account consideration regarding the invested power for doing the pulse or whatever, right? So
yes.
For example, in the GRAPE, so which is your compromise? So you're using that the GRAPE has a peak power which is essentially equal to the peak power of the top hat, or
yes,
or the average?
No, the maximum. I put the cutoff to the GRAPE in the maximum of the top hat. I don't let it be bigger than that one. Okay. But here, I'm not very sure what I was applying, but maybe it did. Here, I think that it didn't reach the maximum amplitude. Okay. These are the pulses, and both X and Y go in the same, exactly in the same line.
Okay, so then this is resilient, more or less, I don't know, 4 megahertz to the right and to the left, more or less resilient, right?
Yes, more or less, yes.
And the maximum is 15 or 20 megahertz?
Yeah, 20 megahertz or something like that. So, now I'm going to put I'm going to put the system in a more complex situation, which is putting it inside a cavity. In that situation, the way that the controls from outside go inside the cavity is not direct. They go with this ordinary differential equation. F are going to be the controls that we input to the cavity, U the controls that are inside the cavity, how the F transfer to inside the cavity, and the gamma is the decay rate of the cavity, which is going to limit a lot what we can do or not inside the cavity, what controls we can apply to the system. And this is the solution of the ordinary differential equation, which I have used for some calculations. So the constraints, what happens is that it is not possible to switch on and off the controls inside instantaneously. So, for example, we cannot implement a square pulse to the system. And this is, for example, the fastest way we can implement a pi pulse, which is all the parameters are analytical, how much it takes from here to here and from here to the end of the pulse. And what we do is apply a square pulse at the beginning. The blue one is the pulse outside the cavity, what we input. And we apply a square pulse with the maximum amplitude we can perform. And here we see how the field inside the cavity starts to switch on. And later, since we want to make it to switch it off as fast as possible, we put the maximum amplitude but with negative values for a certain time until it's completely off. So here.
And then the red is a pi pulse in the cavity, right? So I guess that if
yes.
you integrate the red over time, I guess I go to a phase of pi, right?
Yes, yes. The red is the one which has the phase of pi. Yeah. So here, comparing the red one, how smooth it has to be, and comparing here how it's not that smooth, we can see that the constraints that the cavity, the decay rate adds to our optimization is quite big. So Now what we want to do is to see if GRAPE is able to find some pulse that performs better than the previous one. And for that, we have to see how to calculate the gradient, because now it's not straightforward, because the GRAPE algorithm.
The previous one is the one that everyone is using, right? Or
Yes, I suppose yes. It's the one that Miller was using.
the only reference we have.
Yes. Yeah, I have not. It was just to compare with something, and I took that one. But yeah, maybe it would be a good idea to check with more references. Yes.
It looks pretty well designed. That one.
Yeah, it looks well designed. Yeah. So now what we want to do is to calculate the gradient, and the GRAPE algorithm provides us the gradient with respect to the controls acting directly on the system, which is the d phi over du. But what we want to calculate is d phi over df, which are the controls outside the cavity, the ones we are inputting to the cavity. So for that, we have to do some chain rule and stuff. This is obtained from the equation I have shown before, the analytical solution of the ordinary differential equation. And combining this with this, I'm going to explain. Okay, because the field, another thing that happens in cavities is that at the end of the evolution, the field inside has to be 0, because if not, it's not the end of the evolution. So you can measure there the state, but if it's not 0, it will continue evolving until it switches off completely. So to force it be 0 at the end, I have taken two considerations, which are first, maximize the fidelity for a longer time. That's for the last time steps, say that the fidelity has to be 1, and in that way the optimizer will understand that for that time the evolution has to be performed. And the second one, because with this one it wasn't enough, the optimizer was doing crazy things, and apart from that, I added, I forced the controls to be 0 at for example, the second half of the evolution. This was taken arbitrarily. You can take another, not the second half, but the last third part or whatever. But it doesn't matter much, because later I choose which is going to be the duration of the whole duration of the evolution. So. And okay, this is the maximization of the fidelity for longer time, and adding everything together, we have obtained some results which are not good. Yeah, I have not obtained good results yet. This is the red one is the pulse. Is the robustness that has the pulse explained before, the fastest one. And the blue line is the robustness that obtains the pulse that I have obtained with the GRAPE algorithm. The problem is that the blue one has 5 or 10 times, takes 5 or 10 times longer than the previous one. And I still have not. Well, this is an example. I have obtained more pulses, but no one is good. Gives us a good robustness for the situation. So yeah.
If you go to the previous slide for a second, here what you have when you do the multiplication is essentially a discrete Laplace transform.
What?
What you are doing is the discrete Laplace transform of the pulse, of the derivative of phi respect to uj. So maybe you can also use this in order to work in the other space, and then the transform. So to do the application in the line space,
Yeah.
just do the Laplace transform, and you will get the optimum for this one.
But then you mean to optimize the one inside, and later do some transformation to obtain the pulse outside. But the thing is that then you have to already put a lot of constraints inside, because you cannot do whatever you want inside the cavity. You have some, the curve has to have some smooth behavior, and this is to apply those constraints. What I did was calculate the one outside, and then with the ordinary differential equation transfer to the one inside. But in the other way, I don't see it that easy to force the control inside the cavity have the behavior that it can have.
But you have, so what you have, we connect the inside and outside of the cavity, is essentially, let's say, this is the discrete Laplace transform.
Yeah.
So this is inverted. Just the Laplace transform is inverted, you can go in one direction or in the other. So in principle, you can do the optimization inside and you will always find something outside. Another thing is that what you find outside is physically
yeah, that's the thing.
It's not totally invertible, right? So there is a set of solutions here.
Yeah.
Okay, you have solutions here which always connect the solution in, right? But here you can optimize more if you want, and you don't find the solution.
Yeah, for example, the thing is, you are, in some sense, you are right, you are going to find an inverse, but for example, if the optimizer gives you a square pulse, there is no way you can do it.
No, for sure. I mean, I'm just talking mathematically, in order to reduce the complexity of the minimization.
Yeah.
Of course.
Yeah.
You have physical constraints.
Yeah.
The reality. But in general, I think in this case, I don't know so much about the discrete Laplace transform. The continuous one is invertible for sure. In this case, the discrete, I don't know.
Yes, there will be, yes. I'm sure there is that it's possible, and I was thinking of doing that, but I don't know how to say. I decided not to do it because the constraints were not so easy to force, or yeah.
And then if you start, for example, if you do something like a SIG, right? So you start from the square, which is apparently pretty good, and then you allow for some deviations for the SIG, right? For the
yes,
square.
I did that, and it stayed in that.
It never escapes.
Yeah, it doesn't escape from there. Yeah.
So for the moment, that's the optimal.
Well, at least it's a minima, a relative optimal, not the global one, but it's at least a local minima. I think that it is.
Everything tends to go to, if you do that, everything tends to go to the solution.
If you start from that one, it doesn't escape. It doesn't find that solution either, because I think the landscape, it's a bit complicated.
And that solutions already include the zeta component, or the x and y?
Only x and y.
Okay, that would be the...
Yeah, but for this case, I have also put the Z1, and it doesn't add a lot of like it doesn't add more robustness, or it's also that you are adding another control, so you are adding n more terms you have to optimize, and I don't know. Maybe it's also that the problem.
At least the easy case,
Yeah.
what they said, I think it should be much better.
And then the point is not, sorry, so the GRAPE is not, okay, it's not a question of the algorithm, right? Because GRAPE would be already advanced enough, right? So, because I can imagine other numerical algorithms to minimize, right?
So GRAPE is only computing the GRAPE.
Exactly, so what I mean is that here we have something like a problem that we are not finding anything, and probably it's not because GRAPE, right? Because
GRAPE is just a method to compute gradients in an efficient way.
Exactly.
Yeah. With the gradient is
exactly. So this is what we are not getting anything. So probably there are more advanced algorithms that GRAPE that minimize the other, but that's not the point, right? So the problem is more in that we are not getting the okay.
Yeah, that's it.
Okay, I will continue. Well, the conclusion, so what we have done is introduce the GRAPE algorithm, see an example with a simple model, extend it to cavities, see all the constraints that appear in that cases, and we have not obtained good results yet. And well, the alternatives, it can be adding some randomness, but up to now it doesn't give us experimentally friendly results. Very.
But the results are good or bad with randomness?
Are not good either. Yeah, it's.
If they were good, I think they can be experimentally run, but they are not good.
No, they are not. But I don't know. But maybe there is, I don't know. There are some algorithms which maybe it could reach better solutions, but the solutions would be chaotic. I think very, very.
I mentioned the fact of the set because they were experimentally feasible.
I meant that if they were good, we could do something maybe to convince the experimentalists to make it work.
We can cheat. So I mean, now because I think that what I want to say is that if we introduce the set, I mean, we have a previous experience in which apparently you can really bring more orgasms to the pulses, right? But probably what is happening here is that this gamma that you introduce is killing essentially.
Yes, that's
possibility, right?
Yeah.
Well, even in the case without a cavity,
Well, in the case without a cavity, the set does not. No, in the case.
But we have something in that direction.
Sometimes.
Yeah. We have
yeah.
Strange.
So we had something in the direction that then.
I mean, sometimes it finds solutions, better solutions with set, but it's not the general case.
But that's strange because that case, I mean, probably we can do something even analytical and demonstrate that with X, Y, and Z. Yeah, you can imprint more robustness, right?
Yeah, for this case, I remember that it was put in the set almost in the zero.
So GRAPE didn't.
It didn't find good gradients for set, or I don't know.
Because we found something. I mean, I can imagine that we could get better results there. Even, I mean, can be derived analytically, but then what I think is that if the presence of this gamma kills essentially all the possibilities, because you don't have the power of doing the funny shapes on the controller. Maybe we should start watching that the solution we have analytically and see what happens there, why GRAPE is not converting to them, right?
Yes. Well, yeah, that's it. At the end, optimization algorithms do crazy things, and you cannot control what they do.
Yeah.
Yes.
Yeah.
Yes. Okay. So, thank you.